Welcome to the lecture that covers solutions, and in this lecture we're not going to be talking about problem solving. We're talking about a different kind of solution. We'll first start off the chapter with a little backstory of a type of solution that turned out to be super deadly. So back in 1986, in August, in the country of Cameroon over there in West Africa, there was a village, a couple villages actually, that were just downhill from Lake Nyos, or Nyos, I believe, is what it's called. And we can see a picture of this lake right here. And this lake is basically, underneath it is a big volcanic crater. So, what happened on August 22nd, 1986 is that in this lake, so much carbon dioxide had seeped up from the volcanic activity way down deep that it kind of burst through the water, all right, and started to flow down the mountain. So it was kind of like this quiet little death of creepy, CO2 gas. You can't see it, but it started to creep down the mountain because CO2, as hopefully you recognize or understand, is going to be heavier than atmospheric gas, and so it's just going to kind of hover down along the ground, and down below the crater lake in the valley were little villages of people, and overnight it killed actually 1,700 people, and countless cattle died from suffocation of this CO2 that came crawling down the mountain from Lake Nyos. And so, a few people had escaped, the clutches of suffocation death, whether they were higher above ground or whatnot, is a mystery, but that's what happened. And so now why it happened was a solution of carbon dioxide mixing with the lake water. And there was a disturbance in the water that allowed the carbon dioxide to then be emitted from the lake water in massive amounts. And so and then it started to come down into the valley. Now, this is going to happen continually, and because the lake is still there and the volcanic crater underneath is still active. And so what they've done these days, in 2001, they built this project because they saw that the carbon dioxide levels were rising again. So they did this project where they basically created a geyser within the lake. So a big, huge, long tube with a pump that would start to pump gas from down below the surface of the lake out of the lake, just kind of continuously. So it looks like this little geyser here. It carries carbon dioxide gas away from the bottom and up into the atmosphere so that it's let out slowly instead of this huge, burst at one time that can be deadly. So that's kind of our little backstory for this chapter. And it's an interesting one, and it has to do with solutions. So a solution is a homogeneous mixture of two or more substances. Remember, homogeneous means that you can't see the parts. All right, so it's not obvious as to which two or more substances are making up the solution. So here's some examples of solutions. Solid dissolved in water, for example, salt water. Right, so once this salt here fully mixes with the water, it'll dissolve, and you can't see the parts. You can't tell the salt from the water. We also have gas dissolved in a liquid, kind of like the CO2 that was dissolved in Lake Nyos over there in Cameroon. And so this is a picture of some dissolved gas in liquid, and this gas is actually coming out, so the atmospheric pressure is releasing it, so it's not actually dissolved. You can actually see the parts in that one, but it's an example of a solution where gas is dissolved in liquid. Another a good example of gas dissolved in liquid is actually your own blood. Your own blood has oxygen and carbon dioxide, both dissolved in it, and gets transported around your body. And then you can also have two liquids dissolved in each other, like alcohol and water, or any of these guys here. These colorful solutions are looks like two liquids dissolved in each other. Now, the most common solutions are those that contain either a solid, liquid, or gas that's been combined with water, and that's what we call an aqueous solution. Aqueous solutions are anything that combines with water, and we'll see in a little bit that's because water is the most common substance on Earth, and it is polar, and so it is a very common solvent. So, like in the previous slide, we said that a solution has at least two components, and we can define these two components as solvent and solute. The solvent is the majority component, the component that's in most abundance within the solution. Another way we can think about it is it's usually the component that is doing the dissolving. Like I had mentioned last slide, water is so abundant on Earth that it is the most common solvent in solutions. And then we have the other component, which is called the solute. And that's the minority component. It's the one found in least concentration of the two. And basically, another way you can think about it is that it's the component that gets dissolved. And so, if you remember the like dissolves like rule when we were talking about polarity, not all things will dissolve in each other, so not all things will make solutions. Polar solvents dissolve polar or ionic solutes. So basically polar dissolves in polar and nonpolar dissolves in nonpolar. So that is basically what we see here is polar versus nonpolar, and they're not dissolving. You can see that the water and the oil are not dissolving because they are not alike. Water is polar and oil is nonpolar. Here's another cool example. This is grape juice in oil. And we can see the grape juice little clumps up a little bit in oil because the grape juice is polar and the oil is non. But over here on this picture, this is a molecular view of alcohol being dissolved in water. And both of them are polar substances, so they can interact with each other, having attractions to each other, and can dissolve in each other. All right, so knowing that we know, we can kind of figure out if we're given a list of compounds, which would be, the most soluble or the least soluble in water, because we know that water is polar, right? And so if water is polar, then it's going to dissolve other polar substances. So the least polar would be a nonpolar substance. So out of these four here, CCl4, CH3Cl, NH3, and KF, we got to just figure out which one is nonpolar if we're going to talk about the least. And so to figure out polar versus nonpolar, we have to take a look at the electronegativity differences between the atoms that are being bonded together and the overall dipole moment or pull of electrons in a molecule. So if we take a look, let's do CCl4. So C and then 4 CLs hooked up. Now electronegativity difference-wise, carbon and chlorine are definitely a polar bond. However, you can see that all the chlorines are going to pull in equal and opposite directions. So this guy is non-polar. All right, so that's probably our best bet for our least soluble in water, but let's take a look at the other three just in case. CH3Cl will have carbon with 3 H's and a Cl. And we can see here that the hydrogens are going to form nonpolar bonds between carbon and hydrogen. However, this Cl here is definitely going to pull those electrons. So this is going to be slightly negative on this side. So this guy is definitely polar, so that is not one of our choices. And let's take a look at NH3. NH3. All right, and so we see here that we've got 3 H's and an N that is a polar bond. If we look at the difference in electronegativities, however, we've got unequal and unopposite pulling. All of the electrons are going to go towards that nitrogen. So it's not equal and opposite. So this guy, again, is also polar. So that's not going to be one of our answers. And then last but not least, KF. KF is ionic. Okay, so is definitely going to be a polar substance because it's the electronegativity difference is so great that fluorine is going to totally rip away that electron from potassium, and so there's definitely polar. This guy is going to be, this guy's going to be negative, and this guy's going to be positive. So there you go. That eliminates him. So the one that's going to be least soluble in water is carbon tetrachloride. Okay, so we're going to dig deep. The first thing we're going to dig into is solutions of solids that are dissolved in water. So the first question we're going to answer is, why do some solids dissolve in water and others don't? Like, why does salt dissolve in water and sand doesn't? Well, when we put a solid in water, there's competition. There's competition between the attractive forces that hold the solid together. Okay, we call those intermolecular forces, remember from chapter 12. And the attractive forces occurring between the water molecules and the particles that compose the solid. Okay, and so, actually that's a mistake. That should not say intermolecular forces right there. All right, and so basically what this means is that we're basically going to have a tug of war between the attractive forces, the intermolecular forces between the atoms of the solid versus how hard the water molecules can pull apart. All right, and so in salt, okay, the attractive forces of water win over, and so that's why it dissolves. So we can see here salt crystals dissolving water, that the attraction of water is going to be pulling on the salt molecules stronger, and so the salt molecules are going to be able to separate from each other and dissolve. Okay, so when you put salt into water, it's going to completely dissolve away. Now, on the other hand, sand, all right, this one here is sand with all these little hidden Mickeys of water molecules. We can see that the water molecules don't have enough strength to pull away the intermolecular forces between the atoms in the sand. Okay, so the intermolecular forces in sand are much stronger than water can pull, and so it doesn't dissolve. Okay, water, H2O, can't pull hard enough to get sand apart. All right, so can't pull enough. And so that is why some substances like sand, wax, and I don't know, other kinds of other solids, calcium carbonate and stuff like that, can't be pulled apart because the intermolecular forces win, and so they don't dissolve. All right, so the next thing that we're going to talk about is solubility and saturation. You probably already realized that solubility is basically kind of the ability to dissolve, but we're going to dig a little deeper into that definition and say that solubility is the amount of the compound in grams that dissolves in a certain amount of liquid. So for example, at 25 degrees Celsius, 36 grams of sodium chloride will dissolve in 100 grams of water. All right, and so that's the solubility of sodium chloride. It's 36 grams in 100 grams of water at 25 degrees Celsius. And so we can see if we're looking at a specific temperature, then temperature is going to have a effect on solubility, and we'll see that later. Now, that is what we call a saturated solution, because that is the maximum amount of sodium chloride that can be dissolved in 100 grams of water. So we call that a saturated solution. It's a solution that holds the maximum amount of solute under this, the solution conditions and under the certain temperature. So if we add additional solute to a saturated solution, it's not going to dissolve. All right, so we can see here in this picture that we start out with this amount of solute, and over time it starts to dissolve. Okay, but then it doesn't dissolve anymore. And so at this point, okay, we can say that it's definitely saturated because no more of the solute is dissolving. So that's what we call a saturated solution. The opposite of a saturated solution would be an unsaturated solution. So an unsaturated solution is going to hold less than the maximum amount of solute. So in an unsaturated solution, you can add more solute and it'll continue to dissolve. So, if you have a cup of water and you add a teaspoon of salt and you stir it up and it dissolves, okay, it's probably an unsaturated solution. You could add another teaspoon of salt and it would still, the salt would still dissolve because you haven't reached the saturation level. So that is basically what is depicted here in these pictures, is that we've got a certain amount of solute and over time it dissolves, and if we add more, it still dissolves, disappears. Okay, so that is an unsaturated solution. Typically, you would think that, there's only two options. You either hold the maximum or you hold less than the maximum. You're either saturated or unsaturated. However, in some situations, we can have what's called a supersaturated solution. It's going to hold more than the normal maximum amount of solute. And so if there's any disturbance to the solution, then solute will start to precipitate out of it quite rapidly. And the way we do this, and an example of this was like Lake Nyos over there in the Cameroon. It was a supersaturated solution of carbon dioxide and water. And there was some kind of disturbance where the water started to shake up a bit. Perhaps it was like a little earthquake underneath the volcanic crater, and so it started to shake up the water, and that disturbance released the carbon dioxide in massive amounts. All right, so the way we get a saturated solution is that what we do is we heat up, we raise the temperature, because we're going to find out that if you increase the temperature, you increase the solubility. So if you increase the temperature, you can add more than the usual amount of solute to it, and it's going to still dissolve. So heat it up, add a bunch of solute so it dissolves, and then once that solution starts to cool down, what's going to happen is that you're going to start seeing little precipitates coming back out of it. Or if you disturb it at some point, you can get a kind of like a, all of a sudden crystallization happen, which is kind of cool. That's what this picture here shows. They had a supersaturated solution, and you just shake up the little volumetric flask, and bam, these crystals down here formed. It's pretty cool. All right, same thing here. They took the little tongs here and kind of tapped that solution, and bam, we get this precipitation of the solute out of the solution because it is super saturated. All right, so we're talking about solutes dissolving in solvents, and our most popular solvent is water. So how do we know which solids are going to dissolve? Well, back in Chapter 7, we talked about ionic solids, and we used the solubility rules, or that solubility chart. I had this one in our notes, and then we had another big matrix one in our lab manual. So those are the solubility rules for ionic substances. So if we want to see if an ionic substance is going to dissolve, we can use these rules there in those charts. However, if we're looking for molecular solids, okay, so covalent, like sugar and stearic acid and whatnot, we have to basically use the like dissolves like. If it's a polar molecule, it will dissolve in water. If it's a non-polar molecule, it won't dissolve in water. And so that's kind of a simpler rule for molecular solids. You don't have to look at a chart or anything like that. It's basically like dissolves like. Polar molecules dissolve in water, and non-polar molecules won't. So you've probably noticed, or hopefully you've done a lab in regular chemistry where you dissolve some substances and they are able to conduct electricity, which is pretty cool. These are what we call electrolyte solutions. They are ionic substances or ionic solids that dissolve in water, And when they dissolve, they break apart into ions, charged molecules. And charged molecules of any kind are able to conduct electricity, and so we call that electrolyte solution. Now, if you do the same thing with a molecular solid, a covalent compound, when it dissolves, what happens is that the sugar molecules or the molecular molecules just break apart from each other. So instead of actually breaking apart the actual ionic compounds into ions, a positive and a negative atom, what happens in sugar solutions, okay, is the molecules break apart from each other. So it's just the intermolecular forces, the IMFs, that break apart in molecular substances. Okay, it's not actually the compound itself that breaks apart. So we don't have any charged or free atoms floating around in molecular solids that have been dissolved. And so if we don't have any free atoms that are charged, we're not going to be able to conduct electricity. So those are called non-electrolyte solutions. So if we take a look at the two light bulbs here, you can take a guess of which one is which. This light bulb that's being lit up, all right, is definitely is lit up from an ionic solid that's been dissolved. It's called an electrolyte solution, versus the other guy, the light bulb's not being lit up because this is a molecular solid that has been dissolved in water. So this guy's molecular and no free charged ions, so no light bulb gets lit up. All right, so I hinted at it before, the solubility for solids and liquids is going to vary greatly with temperature. In fact, the solubility of solids in water increases with increasing temperature. That means you can dissolve more solid into warmer water than you can do into colder water. Okay, so as you increase the temperature of a solvent, you can add more solute than regular. Now, we can take advantage of this fact by a way to purify a solid. So if you have a solid that is impure, has little, maybe little speckles in it or something like that, it's kind of dirty, what you can do is a process called recrystallization. It's a common way to purify a solid. Basically, what you do is you dissolve it in water that's at an elevated temperature. Okay, dissolve it in warm water. Create a saturated solution. So you're going to basically dissolve it until no more crystals are able to dissolve. And then as the solution cools, remember the solubility is going to decrease, because if you decrease the temperature, you're going to decrease the amount of solute that can actually be held in solution. So as the solubility decreases, it's going to cause precipitation, and those precipitates are new crystals forming from the molecules or the ions that are dissolved. And so when these new crystals form, they usually reject impurities. So any other molecule, any dirtiness, any little grains of, rock or whatever is going to be kind of kicked out of these crystals. And so your result is a pure solid in the end. And so that is one way we can purify a solid, is through recrystallization and taking advantage of supersaturated solutions, and the fact that when you increase temperature, you can increase the amount of solubility of that solid. All right, so the last type of solution we're going to talk about in this lecture is solutions of gases in water. All right, so we talked about dissolving solids in water. Now let's talk about dissolving gases in water. And the most common, most popular type of gas solution we can think about is a can of soda, right? The carbonation inside of a soda can is gas dissolved in water. Other examples of solutions of gases, lake water and seawater always have dissolved oxygen in them. That's how they, how creatures, plants and, not plants, but animals, that's how they can survive in water. Okay, those aquatic animals are taking advantage of the dissolved oxygen to feed their cells. And plants, water plants, are putting more oxygen in the water. I had mentioned before that a solution of gases is also found in your blood. We have dissolved nitrogen, oxygen, and carbon dioxide in your blood floating around your bloodstream. And then last but not least, just even regular tap water has dissolved atmospheric gases. And you can actually observe those gases when you're boiling water. You always see, if you boil water and you actually watch it boil, A, it'll take longer because that's what Grandma says. But B, you'll see that there's little tiny bubbles that start to kind of be released before it actually starts to really boil. And those tiny little bubbles aren't boiling. It's not water vapor that's actually being produced. It's the release of the trapped atmospheric gases inside of the tap water. And so those trapped gases are released first, and then there's enough energy. When there's enough energy to convert water into vapor, that's when the water actually starts to boil. So solubility with gases is actually opposite of solids. All right, the solubility of gases decreases with increasing temperature. So if you warm up a water or solution, you're actually going to have a decrease in the amount of gas you can hold in that solvent. And so boiling water is an example. If you heat it up too much, then those atmospheric gases are released. But if you got cold water, then they're still there. Another example that I have here is soda. Okay, so warm soda is going to fizz a lot more than colder soda. All right, it's going to be releasing those gases at a lot more quicker rate than cold soda does. So solubility decreases with increasing temperature when we're talking about gases. Now, when we're talking about gases, temperature is always a factor, but so is pressure. Okay, so this is not a big factor when it comes to solids dissolving in water, but when gases are dissolved, pressure is definitely going to have a hand in it. So solubility of gases also depends on pressure. The higher the pressure above the liquid, the more soluble the gas is going to be in the liquid. So here's an example of what that means. If we have increased pressure, okay, so this is the liquid here. If we have increased pressure right above that liquid, basically, we can see that there's really no room for those gas molecules to go except inside the liquid. So the gas molecules are going to be able to dissolve more easily inside of liquid if there's higher pressure. Then if there's lower pressure, then the gas molecules can hang out up here. They're not going to be forced basically in to the water or the liquid part if the pressure is not high enough. So that's what we see in soda cans. Okay, soda cans are put into, they do it with cold water so that it's able to hold more gas, and they force it in and keep it pressurized so that the carbon dioxide is able to dissolve. A lot more carbon dioxide is able to dissolve in the water than if, that's why it's always like filled up too. So the pressure is really increased inside of that soda can. That's what we call Henry's Law. Is the higher the pressure above the liquid, the more soluble the gas is in that liquid. And so that's how that works. All right, that's all we have for this lecture. In the next lecture, we're going to talk about the amounts of solutes in the solution. And so we're going to cover mass percent, molarity, and molality.